All right, these are your video notes for section 6.1. We kick off chapter 6 with the discussion of polynomials. We'll have a little bit of terminology up front and do some visual stuff, and then we'll get into some problems where we are going to base our work on tabling and what kind of functions we'll have. Kind of a snapshot of the list of concepts today. So classifying to start, is it a function or not, and how we know that. The polynomial, is it a function? Finite differences, that'll be our tabling classification. And then writing a quadratic equation from that table of information. So first of all, it's a general form concept, and I'm going to jump down here to general form of a quadratic, which we know from chapter 5. And there's your general form, right? Ax squared plus bx plus c. The definition up here is just largest exponent to smallest exponent, and that's really what's going on here. So we didn't really maybe specifically talk about that in chapter 5. We definitely use the word general form. And we look at a polynomial with an exponent bigger than 2, then we just have to go largest to smallest exponent. So 4, 3, 2, 1 number. Some of these have names like constant, linear, quadratic, even cubic, and then once we get beyond exponent 3, we just kind of start going, well, if it's got a degree 4, it's a fourth degree. The degree means the largest exponent in your polynomial function. So if you say it's fourth degree or fifth degree, you're describing the biggest exponent. This is a fourth degree. And also we can talk about as degree 1, 2, 3, use the actual numbers, but these words will come in and so will the numbers too. So we'll even do a quadratic as a second degree. So you'll see that kind of interchangeably going on. Okay, let's get into what makes it a function, yes or no. And so visually there's some things you can look for. We're going to start with that down here, which is no breaks, no stopping points, no asymptotes. And we've talked about some graphs in the past that have those things going on. So we've actually had some graphs that were... So we're going to look at this short list. We're going to go back to chapter 5, talk about quadratic, then start looking at some other things and see yes or no why they are or not. So let's talk about the idea of some of the visual stuff that we'd be looking for. We're going to go to desmes and just have a look at this set of graphs. So one you're familiar with for sure from chapter 5 is your quadratic, and of course we know that's a parabola for a couple of reasons, we know it's a function for a couple of reasons. It's 1x to 1y, it passes the vertical line test, so we know that's a function. Let's take that one off. Let's look at a fourth degree. Fourth degree actually in some cases looks a lot like a parabola, but again, smooth continuous curve, no breaks. Pop that one back up, same thing, smooth continuous curve, no breaks, no sharp corners, that kind of stuff. So those are definitely going to be functions. Now to give you some ideas of things that are not, here I have this sort of two-piece graph going on. There's like this chunk here and this chunk over here. There's a break in the graph in here. So that would be in the no category. And there's another reason we can determine that without having to see the graph. So you guys won't have to graph to answer this question. We will do some graphing of polynomials that are functions later in the chapter. Check out this one. It's got this kind of funky, kind of comes down and there's that sharp corner, then it comes back up. So that fits in the category of not a polynomial function. And then the last one, which we dealt with in chapter 5 also, which is the exponential, right? Well, an exponential has an asymptote, which means there really is a break because there actually is no graph down here, so not a polynomial function. Let's give you a general visual idea. Let's go back to this, just how you can tell without even having the visual, and that's these things up here, negative exponents, fractional exponents, or exponents that are a variable, which really are ways for you to understand yes or no without having to see any actual graph. So we know that's a yes right there for sure. Visually that was a yes. This one, when I had it actually over here in the desmes, you notice that I had x to the, oh, sorry, I didn't do that. Let's check that out. I thought I brought that in there, but if I bring that up, that exponent up, that's a reason for a no. So if you guys remember working with exponents, I can get rid of the fraction by bringing it up into the numerator, and that makes the exponent become negative, and now you got your negative exponent issue going on. This one might look a little bit weird at first, like is it a square root function, but it's really looking like this. If I go get rid of my third root, or I shouldn't say get rid of it, but rewrite it, it's a 1/3 exponent, and then 2 to the 1/3 is 2/3. Well, now I have my exponent that's a fraction. That's a disqualifier. And then anytime your exponent's a variable, that's a disqualifier. So those are reasons why you would say no, and you can even use those exact wording to explain. Your negative exponent, fraction exponent, exponent's a variable. Otherwise, if those three things are not happening, you're good to go. All right, let's start talking about what we call finite differences. And so another way of talking about it is the difference of differences, which seems kind of strange, but it's a way for you to look at a table of values, again, not a graph, just a table of values, and determine which type you have. And what you really do is you actually work your way backwards through the list and you subtract your y values. So as I go back, I'm going to go 13 minus 11, 11 minus 9, 9 minus 7, and so on. Turns out on this one, they're all the same number. That's all a difference of 2. If your first difference, and I'll explain what a second or third difference might be, because right now we've only got a first difference, but if your first subtraction, let's say, is all the same number, then it turns out you've got a linear function. So what's the slope? Well, this is actually a common difference if we talked about it as like a sequence. And remember that slope and common difference are the same exact idea, so you've got a slope of 2. Your y-intercept, your first coordinate up there is 0, 1, so we can grab that. And then if I know these two things, what's the equation of a line, especially if I'm saying it's first degree or it's linear, my line should be mx plus b. So there's a quick graph of that, but that table of values models a linear function. So what we're trying to do with the differences, those red numbers, is figure out what they tell us. So if your first row is the same, you got a linear function. Okay, now let's see what happens like second and third row. So look at my table of values and I start subtracting my way backwards up through the list. That's why I have my arrow going this way, going backwards. And I list out my differences. Now here, they're different numbers, right? So 49 minus 36, 13, 36 minus 25, 11, and so on. If the numbers are not the same, then you subtract again, but you use this list. So if I do that, 13 minus 11, 11 minus 9, 9 minus 7, and so on. Turns out those are the same numbers. So if your second difference is the same, you then have a quadratic. And if you look at the quadratic and say, well, how is it a quadratic? Check out the first row of differences. Can you pick out a pattern change? And sure enough, there it's saying the first two numbers, 1, 3, 5. So this table, if you graphed it, would be a table that models a quadratic function. All right, let's try a third degree. So do our subtraction again, going backwards through the list. They're different numbers, so that's working my way backwards by subtraction. Do the second set, which is now subtract these numbers going backwards. Still different. All right, now I'm going to do a third set, subtract these numbers going back, and I finally get a number that's the same. So no, not linear, because they're all different. All different, no, not quadratic. All of a sudden, they're all the same. If it's the third difference, it's the same. It's a third degree or it's a cubic. Now that means a couple things. No slope going on here because you're not talking about a line. No pattern change, not a parabola. And if we actually drew that table and saw that graph, it would look something like that. So the difference of differences, or the book will call it finite differences, but the idea is you want to check at which row of subtraction do you get the same number, whatever row you're in. D1 linear, D2 quadratic, D3 cubic, or third degree. All right, let's check out our last problem. This one's kind of our whopper. It's going to take us a couple slides, and it kind of pulls in a bunch of ideas and even some stuff from way in the past you guys may or may not remember. But the first thing to do is see what we have, right? Is it degree 1 linear, degree 2 quadratic, or degree 3 cubic? And typically it won't go out any further than that because it just gets to be like a little too much for one problem. And we figure at this point you guys have figured out the idea. So going again backwards through the y values, do my subtraction. My first differences are not the same. Now backwards again through that set of values. My first differences are the same, which means D3, I'm done. This is quadratic. So at second degree, it's quadratic. Now the question is, what is the equation of that? So like when we did that slide with linear, and I said, well, what's the slope? What's the y-intercept? Let's go ahead and write y equals mx plus b. Well, if it's quadratic, it turns out we can do this. It's just a little more work to get it set up. So we're going to kind of jump through like multiple slides here to help piece this all together because it takes a little more space than what I've got here. But let's see how we can come up with that equation. And to come up with the equation, the things I'm going to need to know are what are a, b, and c. Like when you do y equals mx plus b, you need the slope and you need the y-intercept. When you do general form for quadratic, you need to know what a, b, and c are because those are your constants, or I should say your coefficients. Okay, it's a little bit kind of funky at first, but you guys are going to notice something real quick when I get over here as to where this problem is going. So you take your coordinates. I usually try to grab the first three in the table because the numbers are smaller. And so I've got the table going this way just to kind of help you guys see it in different formats. But there's my x's, my y's, but there's a coordinate, there's a coordinate, there's a coordinate. So I got the first three coordinates listed out. And then what I'm going to do is take the general form equation. I'm just going to put y at the back. And I'm going to drop in the x value, and the y value from the coordinate. So we're going to drop those in for each one. So what's happening here now is I'm trying to create actually a system of three. And we did systems of three back in earlier chapters, like in first quarter where we had x, y, and z. We're going to create an ABC system. So what I'm going to do is start cleaning up the mess here. So we got our x's in. X is 1, 1, y is negative 4. X is 2, 2, y is negative 2. X is 3, 3, y is negative 4, and that's just dropping in from our coordinates. And then all we're going to do is get rid of all these parentheses and clean it up. So 1 squared is 1, b times 1 is 1, so you get a, b, c, negative 4. 2 squared, so there's your 4, 2b, c, and negative 2. 3 squared, 9, and times 3 is your 3b and your c. And so really you're dropping in your coordinate x's for the first two spots. You're dropping in your coordinate y values, get this cleaned up, and you create a system of 3. Now for the rest of the notes, we're going to go through how we get that system of 3 down to a system of 2, down to a single variable, then back our way up and go through that process that we did in previous chapters. So let's finish the problem out. So what we're going to do for starters is do some combining of the equations. We got to go in pairs. So we're going to take pairs. We're going to start with black and red as one. We're going to do black and green as another. The reason I'm using black in both is because it's the simplest equation. With an A, B, and a C, I would always grab that one and combine it with the others. Then the idea is let's start eliminating the variables. So pick one to get rid of. Now to me, because they all have plus C in them, that seems like the easiest way to go. So I'm going to multiply the top equation by -1. That's going to create a new equation up top, which I'm going to change to blue, but all I did was basically run a negative sign through there and change the sign on both. And then what I do is I add them down in columns. And what you'll notice here is the C's are going to drop out in both spots, and that's the goal. Get your system of 3 ABC down to a system of 2. Then I take the 2, if you guys remember how this works, and I drop them into another system. And the idea is get rid of another variable. Well, I think B is probably going to be easiest because I can just multiply this by -2, and that'll cause that -2, +2 to drop out. So distribute -2 in, that creates this one, add down in columns, and now I got my A. And once you get this far, you're pretty much home free. You got to back your way up to the problem a little bit to get the other variables, but here's how it's going to go. So I'm going to take that 2 and plug it in. I'm plugging into this one. I could have plugged into this one, by the way. I just chose this one because the numbers were a little smaller. Gives me my B value. Then I take my A and my B, and I plug them back into one of the 3 originals. I just picked this one because it was nicer. Again, smaller numbers. And get my C. Now that I've got my C, I've got my equation. A, B, and C is what I had to figure out because those are the things that got to be replaced with numbers. Those are your coefficients. And then you're going to get one more question. The homework's going to ask you to find y when x is 12. So it's like if I ran this table out a lot further, instead of trying to follow the pattern so much, if I had the equation, I could just plug in. So I just plug in. So I plugged a 12 in for my x. Calculate there's the y if I was going to continue the pattern out on the table. Now I will admit this problem's definitely got a lot going on. It's organizational for sure. And if you have a video up, I think while you're doing the problem, you kind of just pause and go step by step, you're going to be good there. And that's going to do it for your 6-1 video notes.